everyone. A warm welcome to one and all as we gather for the second lecture of our much-awaited Leadership Lecture Series. Today, we have with us Dr. Ashok Krishna to shed some light on the topic long-duration energy storage. We are excited to have you join us for this enlightening lecture that promises insights and inspiration. Today, we are privileged to have with us another distinguished alumnus who is shaping the thermal mechanical energy storage industry in India and beyond. Dr. Ashok Krishna, the chairman and co-founder of Teams LLC, brings in a wealth of experience and innovation to the table. With a background that spans industries and continents, including decades in Chevron and Babco board, Krishna's leadership has been instrumental in driving Teams LLC's success. A true academic luminary, Krishna's educational path reads like a roadmap of excellence, from the hallowed halls of IIT Madras to the internationally acclaimed University of Massachusetts, Amherst, and the University of Pittsburgh. So ladies and gentlemen, prepare to be inspired, to be captivated, and to witness the inspirational session as we warmly welcome the driving force behind Teams LLC's triumph, Dr. Ashok Krishna.
Thank you. Wow. Man, that's quite a setup. Anyway, now I have to live up to this inspirational introduction she's given me. So I graduated in 1974, went to the US right away. Mrs. Gandhi came for the commencement. I wasn't here. I was already on the plane. Did a master's for a year, but my claim to fame is my PhD took about 21 months. And if any of you are chemical engineers, there's a chapter in one of the chemi books right out of my PhD thesis. Joined Chevron right away, worked straight for 40 years in one company all over the place. Retired as head of technology for Chevron. I retired in 2018. And I took 2018, most of 2018, I goofed off, played golf, watched the entire season of Netflix in one day. And then about 6 months later, I got bored. I said, I can't do this. I've got to do something useful in my retired life. So I'm doing two things. I mean, I'm doing lots of things, but two important things. In fact, I'm consulting with some of the IIT Madras startups. I was late because I was advising the CEO of a company called Planis that does underwater inspections. And I got stuck in traffic in his office. I just came from there. I'm also advising a company called Detect in the US. So I'm quite busy with that. But my real passion is two things. One is waste plastics. So I'm working with a company that has one of the best processes for recycling waste plastics. But the other big one is energy storage, right? So it's a very long deck. I'm going to zip through a lot of it. Stop and ask me questions. There is no flow. I can stop and move along anytime you want. So feel free to ask questions. I am going to go very fast so that there'll be time for discussion if you want. So I'm going to talk about the current state of renewable energy penetration globally. So I'm going to talk about what does the world need in terms of long duration energy storage and why. What are the different options for it? You've all heard about batteries. IIT Madras is doing work on batteries. Batteries are good for about 2 to 4 hours. So what do you do beyond that? So, India is building up 450 gigawatts of renewable energy, mostly solar, which is 8 hours in some places, 9 hours, 10 hours in other places. Batteries will give you 2 to 4 hours optimally. After that, the costs go up exponentially. So how does one run a plant 24/7 on renewable energy? How do you have a grid in India that gets up to 40, 50% renewable energy so that you can function on renewable energy? What that says is, even if you have 10 hours of sunshine, the other 16 or 14 hours, you have to find storage. If you don't, you're going to be reliant on fossil fuel plants forever, right? You got to break the log jam. So that's what I'm talking about. So I'll talk about 4 categories. There's a lot here. And I'm going to skip some of these in the interest of time. And then I want to say a little bit about my startup. If you don't mind, I'll talk about, hi, Professor Narasimhan. You are actually mentioned in my slides. So good timing. So I'm going to talk a little bit about my own startup, the last 10-15 minutes of it. And it's not the one you are aware of, Shankar. It's a different startup. Okay, so let's jump in. So unfortunately, I think this is a PDF. It's not the PowerPoint because this is an animated slide, so you can't see anything. But basically what it says is you go from 27 watt hours in the world today to about 95 petawatt hours. Right? That's where we have to be in 2050 in order to meet the 1.5 degrees centigrade scenario. Right? You all know what that is. It's the Paris thing, right? So if I had a PowerPoint, you would have seen the animation, and you would have seen how renewable energy also grows and fossil fuel goes down. So a petawatt hour is 10 to the 15 watt hours, right? So it's a gigantic amount. No, it's okay. Well, you can if you want. This is the only animation, don't worry. Nothing, there's no other animation. So just trust me, this is about 25 petawatt hours, and this is about 90 something, right? That's what we have to do. We all know that. Yeah, so we all know this, right? Solar and renewable energy costs have come screaming down in the last 20 years. We all know this. So we're down to dirt cheap, right? I mean, in the Middle East, it's 1 cent a kilowatt hour. In California, where I live, it's 4 cents a kilowatt hour. It's practically almost free electricity, right, from solar. That is an amazing transformation in the last 20 years, right? We all know this. We know that this is the renewable energy cost has come down. Move it up. Okay, so there you go. See, I wasn't lying, right? 27 to 90 petawatt hours. I knew my numbers. And the renewable energy goes from about 28% today to 91%. And the fossil fuels have to go down to 5%. This all has to happen by 2050. You guys are all young. You'll see this happen. This we've seen. Okay, I'm going to skip this slide. Basically, it says, when I was growing up, the electricity system was pretty simple. There was a source, and you sent it to buildings and factories and stuff. Now, you got a geothermal plant, you got a high-efficiency building, you got energy storage, you got a plug-in car, you got smart substations, so it's going to go all over the place, right? Smart grid. So life's getting complicated, right? You guys know this. Okay, this is an interesting slide I want to talk about. So when do we need more hours of storage than a battery? Right? That's an important question. What this slide suggests is you can get by with about 4 hours till you're at about 25% on the grid. You can get by with battery storage alone. The minute you go up to 30 to 40%, now you're going to need more like 6 hours. And then when you get to 50 to 60%, you get up to 10 hours of storage. 100% grid, of course, you need lots of storage, right? So where is the world right now, and where is India today, right? So it's a tough chart, and I'll have to tell you what it says. So for example, it says India, this color is about 20%. India is at about 20%. USA is at about 22%. You can see that here, right? Australia is 30. China is about 30. And Canada is at about 67%. So you wonder, what are all these dark areas, right? They're all hydrothermal power, right? So Afghanistan, of all places, is 86% because of hydroelectric. There are lots of dams, right? Similarly, if you go over to Iceland, I don't know if you've been there, I've been there. There's geysers everywhere, and geothermal and hydroelectric. Greenland is all hydroelectric. And in Europe, you can see there's a bunch of hydroelectric. So anywhere you see dark, it's hydroelectric, it's not solar or wind. The guys who are doing solar and wind are kind of at 20, China is at 30, right? So that's what it's saying. So we're right at the cusp of needing more than batteries, right? We're just moving into that. So, won't move. There you go. So I'm going to skip this slide because what it says is another illustration of, well, maybe I'll talk about it. So this is a diurnal cycle. This is in Arizona, in the US. So sun comes on, you charge whatever the heck your storage system is, you charge it, and then the solar energy climbs up, and at this point the sun stops shining. Boom, you're done. Now you got all these durations until the cycle starts again. So here's 1.2 hours of something, 3-hour battery. Now you need 6 hours of something and 10 hours of something in order to get there, right? We don't have any of this. All we have now is this stuff with batteries. Similarly, if you look at a calendar cycle, this is a full year, again in Arizona, and Arizona is picked because it's a sunny climate, kind of like most of India, right? So you can get, here is hydro plus renewable, the nuclear is the gray, here is solar, and then you need battery. Solar per 4 hours, solar plus 12 hours, still doesn't get you, right? There are months in a year that even 12 hours of storage is not enough. We're starting to get to that point in high solar conditions already. And I'm going to skip this one. This is an acute case in California. Believe me, it's true. Okay, so what are the choices we have, right? So batteries are here. Batteries are pretty cool. They're good for, I think this is very generous. Batteries are good for 2 or 3, 4 hours, not even that much. This is the one I'm going to talk about, compressed air. I'll tell you what that is. Pumped hydro. How many of you know what pumped hydro storage is? Does anybody know? What pumped storage is, you have a mountain, you have a lake at the bottom and a lake at the top of the mountain. When the sun shines, you pump the water up the mountain, right? And when the sun stops shining, the potential energy, the water flows down and generate power, right? The problem is geographically, you have to build it next to hydroelectric dams, which is what India is trying to do, right? And then hydrogen is the big unknown. Everybody talks about hydrogen. I don't know about it. We'll get there in a minute, right? We'll talk about it. This thing doesn't move very quickly. Okay, so what the Department of Energy, the Pacific Northwest Lab puts out a report every August. This is 22 August. And they basically say that the cheapest form of energy at scale, if you want to build 100 megawatts and have multiple hours of storage, it says the cheapest is compressed air energy storage and pumped hydro, right? That's what these guys are. The batteries get very expensive, right? Lithium-ion batteries just take off in cost after a point, okay? So it's one of the cheapest ways to do it. Looks like it takes 3 presses. I'm going to skip this one. This is about a lot more detail. I don't have time to read. Okay, so the requirement for long duration storage varies by region, right? So the US is at about 30% on renewables. It's only 22% nationwide. California is at 30%. The US on the whole is at about 22%. But California is leading the way in most things that are green. They want 50 gigawatts by 2032 of storage. 2 gigawatts have to be long duration and 4 gigawatts by 2045. If you ask me how many gigawatts of long duration storage they have today, 0. Right? So the California is desperate, right? They can do 15 gigawatts of batteries if you want, but how do you get 2 gigawatts of something longer than batteries? They got nothing, right? So they're desperately talking to us about what we're trying to do, right? There's billions of dollars being put out by the Biden administration, and I'm hoping to get a chunk of it. I'll tell you in a minute. And right now, the only ones that are there are some flow batteries. There's a bunch of thermal technology I'll talk about. There is compressed air. There's gravity stuff, which is crazily ridiculous. And then there's some non-lithium ion type of batteries, right? And then hydrogen is in the future. Everybody says hydrogen is in the future. This is very slow. So this is in Europe. Europe is more about geothermal, hydrothermal, also some batteries and pumped hydro. They have the most pumped hydro. Europe has got about 97% of their storage from mountains and hills where they've exploited pumped hydro. I'm going to skip a couple of these next slides because it's taken a long time to change slides. Maybe I should sit there and do it, or have somebody sit there and do it for me, because this isn't going very well. See if we can get her to come. Yeah, see, this is, okay. So UAE, Saudi Arabia, I'm going to skip. See, now it's going fast the minute you call for her. Okay, so China, of course, is doing everything, right? They're all over the place. They've got wind, solar, nuclear. They have compressed air. They got everything, right? What they're pledged to do by 2060, net zero, and the fossil fuels will decline, and low carbon will come up. And look at their renewables growth rate, right? This is what they're projecting, right? This blue-green is solar, this is wind, and this is some other stuff. So they are just massively ramping up as like only they know how to do. So India, right? So what are we doing? So we've got 70% of our energy coming from coal. You all know that, right? That's why it's a bit funny for me to see all these electric vehicles. As long as you get electricity from coal, what are we doing, right? Okay, pollution is less on the road, but your electricity is coming from the worst fossil fuel on the planet, right? The most carbon dioxide. So I don't know about that, but I think Prime Minister Modi has said net zero by 2070. He wants to build 450 gigawatts, right? Currently, batteries are 2 to 4 hours. Long duration storage is pumped hydro. It's the only thing being looked at. I'm trying to introduce this compressed air business. I'm talking to folks in India. And that's what's going on in India. Go ahead. So there are four primary forms of energy storage. Electrochemical is batteries, and you all know about it. I'm going to skip that battery topic. Thermal is an interesting one. I'll tell you a little bit about thermal. Then mechanical is the other one, where compressed air is a part of it. And then chemical is hydrogen and ammonia, right? By the way, when I retired 5 years ago, I had zero knowledge of this subject. Okay, this is what I've gleaned in just the last few years of my startup. Yeah, go ahead. And I think this is batteries. I'm not going to talk about batteries, except that China holds 63% of all the raw materials. They're kind of screwed if you depend on them. And all the manufacturers are largely Japanese, Korean, and Chinese, right? You guys know this. Go ahead. Now, this one is put out by the Department of Energy just this month, actually, in early August. And what they're pointing out is batteries are fine, but what they plot is low to high supply risk and the importance to the energy business, right? And basically, red means critical, green means not critical. Look at the stuff that's critical when it comes to batteries, right? Of course, lithium and nickel, but look at all this: cobalt, graphite, gallium, platinum, all this stuff that China largely controls, right? So that is the problem with battery solution alone, is that you're going to be stuck with these materials that are hard to get, right? And there's something called a flow battery that's always been there. It's supposed to get up to 10 hours, but I haven't seen it yet. So go ahead. I'm going to skip this one to go to the next one. So the big news in America is a company called Form Energy. It was invented by a Chinese professor in MIT. And what he did was he dusted off a 50-year-old technology, which is basically iron-air batteries. His idea was air is free, iron is cheap. And what they do is, the idea is to, he says, rusting the iron and derusting the iron in the cathode and the anode. You let the iron rust, and then you derust at the other end. Seems very simple. They have raised $1 billion with this idea, okay? They are building a $760 million factory to produce these batteries in West Virginia. And this is the talk of the town. They've raised a lot of money, but the jury's still out on this very old technology. The reason why it's been revived is it was worked on 50 years ago, and the energy density of this battery was only about 350 watt hours per kilogram. These guys have got up to about 1200, 1250. So they've got to pack the energy density. We are all watching it. If this succeeds, it's wonderful, but it's a lot to ask for. Go ahead. And then, of course, our own folks, right? So this is Professor Chandran and his team. They're working on zinc air battery here in IIT. How many of you know about this in the room? 1, 2, 3, 4, of course. That's not good, guys. You need to know what we're doing here. So this is some pretty good stuff, zinc air battery. It's kind of like the iron air battery, except that iron's being replaced with zinc. Still a cheap material. Really nice work being done by this team. You should look it up. And then there's a bunch of other people working on in India that I won't go into. Go ahead. And this is a company I'm consulting, and they're building a lithium sulfur battery, which is an interesting one. I'm consulting with this company. They claim all kinds of benefits. It's still lithium, but they don't need cobalt, nickel, manganese, and all that. Fine, that's okay. And then this is one I'm familiar with. This was built in Abu Dhabi. It's called a sodium sulfur battery. Again, it doesn't need lithium. It's got a bunch of advantages. No lithium or cobalt, right? The problem with this thing is liquid sodium is incredibly reactive and it's explosive. So you can see they have to have two separate compartments and make sure that the lithium, the sodium chamber never sees anything outside that, right? So it scares me that you can't scale this up. You don't want to build something that's inherently unsafe. Not that lithium batteries are all 100% safe. They catch fire, as you know. But this is pretty unsafe to me. So, okay, so thermal, right? This is an interesting one. So I've talked about batteries already, right? That's electrochemical. The second type of storage is thermal, right? You know what thermal is, right? Hot and cold. So there are a bunch of people. There's an Indian lady called Ramya Swaminathan, who's the CEO of Malta. She's raised $86 million. And it's a very old technology, right? So molten salt is very old. Canada has been doing this for 30 years. So again, when the sun shines, you store it in the heat in the form of molten salts. And then you also have the coolant side. And then you take that heat and turn it into electricity. And that's one way to do it. Their costs are going up. They're struggling, actually. It's a tough thing to do. Molten salt is not easy to manage. There's a couple of companies. There's one called Rondo. There's one called Antora. These are both in California. Their idea is to take a wire and stick it in a brick. One guy is a cement brick. The other guy is a carbon brick. And they claim that they can heat that brick up to 1200 to 1500 degrees centigrade. They're generally pretty good insulators. And so when the sun shines, you heat the heck out of these bricks. And the sun stops shining, you convert that heat into electricity. They've raised a bunch of money, which is amazing to me, right? So these guys are going on. And then the other side of it is the cold side. There's a company in Israel called Nostromo, which takes energy when its renewable energy is available and makes ice, basically. Ice and ice slurry. So you can either take the energy and make hot stuff, or you can take the energy and make cold stuff. And guess who else is doing it? Professor Satya Sheshadri here in IIT Madras is doing it. How many of you know about this? Anybody? Oh my gosh. What Satya has done, and I've toured this laboratory, right? I come to India 3 times a year. I toured this laboratory. What he does is he takes renewable energy and makes ice slurry, which is pumpable. It's even better than ice, right? If you form ice, you got to then chip it and make it into something that will flow into a pipe. Professor Seshadri comes up with this ice slurry, and he is able to circulate that ice slurry, and he has air conditioned. So that's the setup outside the building here, and his entire building is air conditioned with his own process, right? Excellent stuff. I would urge you to go and check out his lab. He's done it himself. He's trying to now commercialize it. So that's one other way to do it. Go ahead. And then this is the one I don't like at all. It's the dumbest thing I've ever heard, right? This thing on the top, a company called Energy Vault. Their idea is when the power is cheap, you raise bricks as high as you can, right? And then when the sun stops shining, you drop the brick and create. That's their whole idea, gravity, they call it. They couldn't get money and build a plant in America. So I met the guy who's on the board, a guy called Eric Fang, Chinese guy. He has built this monstrosity outside Shanghai, this thing, right? Every one of these blocks needs a crane to lift the brick and drop it down again, right? Extremely expensive, and to me, not very clever, but hey, people have thrown in money. I think Goldman Sachs put $250 million into this monstrosity. Go figure. I don't get it. Now, there's another company that kind of has the idea that I have, which is use idle oil wells. But they're dumb too. So you take an idle oil well, there's a casing in an oil well, they want to drop a brick in the casing, right? That's how they want to create. Basically, it's the same idea as the one in the top, except rather than build up, drop it down in a hole in the ground. The problem is the casings are not linear. You drop it, it's going to get stuck somewhere on the way, right? These guys have raised a bunch of money. I don't understand it anymore. But the VC system in America is crazy. Okay, here's the pumped hydro I told you about, right? There is the lake at the top. This is a solid pumped hydro plant in Europe. This is how it's supposed to work. You have a big mountain, a lake at the bottom, and a lake at the top. When the sun shines, you take water from here and pump it up to here. When the sun stops shining, you simply take the water, potential energy, and you generate power. It's good round-trip efficiency, 80%. Problem is you need a mountain and a couple of lakes, which is a little hard to get, right? So my idea is there are a whole bunch of abandoned oil wells in America, right? And these things have unlimited storage where the oil used to be. 150 years ago, we drilled a hole. All the oil is gone. There's nothing there left, so people walk away. So here's an abandoned well in Central California. The operator didn't fix it up properly. When the oil prices fell, he just walked away. So now you have an opportunity to store energy, unlimited amount of storage space in an idle oil well. That's the concept that I'm peddling, right? So I don't know if it'll work or not. We'll see. Okay, this is the other guys that also are looking at oil wells, but equally bad idea, right? You can compress air. It's a compressible fluid. You can compress it to 75 bar, 100 bar. You get energy density. These guys decided to do what they call reversed pumped hydro. Rather than a mountain, why don't we pump water underground? Okay, water, as you will remember, is an incompressible fluid. It cannot have much energy density. So the first time they pumped water underground, it leaked out and it all went away. Bill Gates funded this, by the way. So they raised 10 million, did an experiment, the water disappeared. So now they're going to drill their whole hole to make sure that it doesn't disappear. And Bill gave them another 10 million. And the energy density of the water is such that I don't know how much energy you can get out of drilling these holes. And if you drill your own hole, you're screwed because the cost is very high. You won't get permits, right? So this is another bad one, but there's Bill Gates himself, right? Looking at their, and he's put 20 million down. Good luck with that. It's not going to work, I think, but. Okay, this is the one I'm interested in, right? So 30 years ago, well, in 1978 in Germany and 1990 in Alabama, 2 plants were built, okay? Siemens built it at the time. What you do is you take air, which is free. When the sun shines, you compress the air to 75 atmospheres, 100 atmospheres. Once you compressed it, you take it, and in these 2 cases, they dug a cavern. They dug a hole underground, and you store the air underground. When you need energy, you bring the air up. It goes through an expander. So you can see this is a compressor and expander building, right? And the problem is that when you bring the air up, it wants to freeze, right? So what these guys do, they compress the air, didn't store the heat, stored the air underground. You expand the air, and now you burn it natural gas to keep the air hot. Otherwise, it'll freeze, right? Herr Linde made liquid air by freezing air, right, 150 years ago. The problem with this is you cannot ban natural gas anymore and call it renewable. That's a problem. Second, if you don't store the compression heat, your efficiency is pretty poor, right? So our idea was take the same concept, it's all proven, but store the compression heat, make it adiabatic instead of diabatic, make it adiabatic, do not burn natural gas, but take the stored heat and heat up the air when it expands. Does that make sense? Compress the air. When you compress the air in three-stage compressor, it'll heat up. You need interstage coolers. Take the heat, store it in a hot water tank, put the air down below. In the evening, when the sun stops shining, bring the air up, expand it for 14 hours. But when you're expanding, the air wants to freeze, but I've got hot water stored. It's good for 24 hours. I use the hot water to keep the air hot, and the hot water becomes cold water. It goes through the cycle, and the air produces. My round trip efficiency is now 68 to 70% because I'm using that compression heat. These guys weren't doing it. And half the energy was coming from burning natural gas. What is the point of that? That's not a renewable plant, right? So this is the basis of what we are trying to do. Go ahead. I'll skip this one. Let's keep going. There's another company. There's only one company in the UK, and Professor Narasimhan knows about this. We've talked about it, that has said, I don't want to find holes in the ground. How about if I liquefy the air? If I liquefy the air, the liquid air is 1/700th the size of air, right? So you can compress it into a liquid. It holds huge energy density, right? So then when I need the energy, I will vaporize the air, turn it into regular air, high pressure, expand it. So that's their idea. The only problem with that is now you've got cryogenic setup, right? So it's not just compressing air. Now you have to go through refrigeration cycles and actually liquefy the air. Then you've got to heat it up and expand it. You can do. Then the 2 edges are basically compressed air storage like I'm talking about. In between, you need refrigeration and cryogenic storage. So the costs double. The good thing about though is that you don't have to look for holes in the ground. You can build this anywhere. So these guys have built plants. So that is a BOC supplied liquid air container, you can tell. And these guys have built a bunch of plants in the UK, and they're very happy with it. No one else is doing it. The only ones that could do it, Professor G. Venkatratnam here, wrote the book on mixed refrigerants you need to use here. So pre-COVID, I came and met him. He had already built a liquid nitrogen pilot plant here, okay? And I was talking to Professor Venkatratnam and Professor Shankar Narasimhan, who's sitting here, saying, why don't we turn that into a liquid air pilot plant? I mean, we still want to, but COVID came in the way. We haven't done it. So my idea is to duplicate this in IIT Madras, right? It's a little bit more expensive, but it's independent of any other requirement. It doesn't require a mountain. It doesn't require a hole in the ground. You can build it anywhere. Generally, it's probably not a big scale. It's probably 5, 10 megawatts. You can't build huge plants with it, right? So I'm still hopeful we can do something in IIT Madras with Professor Narasimhan here. Go ahead. Okay, so this is a controversial subject. These are my opinions only. You can argue with me later if you want. The whole world is agog about hydrogen, right? India is going to do green hydrogen. Tata is getting into it. Everybody's talking about hydrogen. Hydrogen for transportation makes perfect sense, right? So right now, to make hydrogen out of water in an electrolyzer is about $6 a kg. You got to get it down to about $1 a kg, 1/6 the price to make it economical. But that's happening. Like solar electricity, this will come down in cost. I think that'll happen. Once you do that, then you can put this hydrogen into fuel cells in cars, right? You know there are a Toyota car, there's a BMW car that runs on hydrogen. And the way they do it is they have a high pressure hydrogen tank compressed to 600 bar at the bottom of the car. Hopefully you won't have an accident, but it's pretty thick walls. And that hydrogen supplies a fuel cell and the car runs on a fuel cell. It's not EVs, okay? It's a hydrogen fuel cell car. Those cars exist. Down the road, they can do that for trucks. Just everything gets bigger, right? And I'm okay with that. There are also people trying to replace the internal combustion with a hydrogen combustion engine, right? So Chevron's doing this too. Instead of a direct ignition, spark ignition IC engine, it becomes a compression ignition engine. So diesel cars are what's called a compression ignition engine. There's no spark plug. So you compress it to a high enough pressure that boom, it lights itself. That technology is being adopted for hydrogen now, right? So if that works out, I'm okay with it. Build hydrogen engines in cars. The efficiency is terrible, but you can do it, right? It's green. What I don't agree with, and I think it's a terrible idea that people are trying to do, is trying to do hydrogen for the grid electricity. So you take solar electricity, make hydrogen out of it at very high cost, then you have to compress that hydrogen to very high pressure and store it underground, none of which has been done. You don't compress hydrogen more than about 200 bar in our refineries and chemical plants. You have to compress it to 500 to 600 bar or liquefy it in order to store it. And if you're able to do all that and not have safety issues and not leak the hydrogen, then you have to burn that hydrogen in a gas turbine, right? Right now you cannot burn hydrogen in a gas turbine, and Mitsubishi and Cummins are saying in 20 years they'll have 100% hydrogen burning gas turbines. To do what? To produce electricity. Why would you take renewable energy electricity, go through all this nonsense to produce the electricity? You know what the round trip efficiency of this whole shebang is? 19%. So why would you, if you want to do grid scale hydrogen for electricity, it makes no sense to me. Hydrogen for transportation makes sense. And I think Nikhil may take me on later on, we can talk about it, okay? Okay, there's some other things. Yeah? Well, just go back one. The even worse idea I've heard, and somebody's doing this in England, is what they call electrofuels. This is the even worse, right? I'm going to sit down. What this is you start, there's a company called Aeon Blue. They want to start with seawater electrolysis. Okay, that's not easy because you got all that high salt content. Use wind energy, do seawater electrolysis to produce hydrogen. Then you take CO2 from direct air capture. There's only 400 ppm CO2 in air. It's about $600 a ton to get CO2 out of the air. And the Biden government just put $1.2 billion in to do it in the US. Good luck with that. That's even Al Gore agrees it's a bad idea. Think about that, right? So when you've done that, now you take the CO2 and convert it to CO. Then you combine the CO and the hydrogen to make syngas. And then you take the syngas and make fuels, drop-in fuels. I spent 10 years of my career taking syngas to make fuels. It's the most expensive way to make fuels on the planet, right? Nobody will ever do it. Forget these steps. You wouldn't even do syngas to fuels. It's too expensive in my mind. And these guys are getting money to do all these steps, right? So what I figured out is there's no logic in all of this. People are throwing money at things without asking the question, does it violate the second law of thermodynamics? And will it ever make money? Nope. Those questions are not being asked, right? Go ahead. Skip this one. Keep skipping up. Skip this. Skip that. Skip that. Okay. Now there's just enough time to talk about my startup, right? Just bear with me for a few minutes. I'll tell you what I'm doing. So I came up with the name Thermal Mechanical Energy Storage. So it's a nice ring to it. It's called Teams. And our goal is nothing less than 24/7 dispatchable power. Dispatchable means you can dispatch that power anytime you want, right? It's not curtailed for several hours or anything. 24/7, can run on renewable energy. We use off-the-shelf surface equipment, compressors, expanders, heat exchangers, hot water tanks, are all off the shelf. We repurpose subsurface infrastructure where oil used to be. Highly scalable, right? We can go to 400 megawatts easily. It can enable 100% renewable power for the industrial operations today and enable 100% renewable grid in the future. So how do we do this, right? Go ahead. So me and my co-founder happens to be a guy who spent all his life in the oil industry looking at the subsurface. We call it upstream, but it's really, that should be called downstream. But upstream in oil business is how do you drill for oil? How do you maintain these wells several thousand feet below? He knows all about that. I don't know much about that. I know how to build plants on the surface, right? So we were a good match. We formed this company about 4 years ago. And Professor Narasimhan, this is not the company I was with in the beginning. We both started with the company earlier called EIC, and they had some issues and some technology development had to be done. They were going for 100 hours of storage. What we found out was, as I showed you in the first few charts, the world does not need more than 10 to 15 hours for the next 20 years. So why should we do a startup to try to get 100 hours? The world doesn't need it. So we both quit and started our own company, Teams, and we've been at it for about a little over a year now, right? Go ahead. So the idea is you got depleted oil wells, decades of subsurface knowledge, right? Every oil company knows the data logs on all those wells that are now become idle, but you have detailed data on the rock porosity, permeability, you have all that data, right? So right now those wells, many of them are leaking methane, which is 30 times worse than CO2. So the idea is you go and plug it off, stop the methane leak, plug off the layer where the oil used to be, and now store compressed air, right? That's what we're trying to do. The gas can be air, it can be natural gas, eventually CO2. So this just says that the US has, how many oil wells? What are they saying? 3 million oil wells that are abandoned, and a chunk of them, right, are leaking methane, right? Methane emissions from abandoned US wells, right? Equivalent to 8 million CO2 equivalents a year, right? Major problem. The Biden administration is trying to solve it. Go ahead. And skip this. And so what we're doing is, all through California, the blue dots tell you where all the abandoned wells are, okay? So we are right here in the Central Valley. So I live just right there, okay? I live just west of Oakland. I've lived there for 25 years now. And Los Angeles is here. So right in between is where the huge farmlands are, the San Joaquin Valley, right? And this is where a lot of the solar plants are going in. It happens to be the place where many of the abandoned oil wells are, right? They're sitting there, 10,000 of them not being used. And what we are trying to do is this simple schematic compressor. You get wind or solar energy, and off peak, you compress, put the air in a pocket, and think about three-dimensionally, this thing runs in for miles and miles, okay? It's contained by water on one end and contained by rock on the other, and it comes out to you and runs for miles on end, right? Huge porous space. And in the night, you bring it back up, you have a generator to generate electricity. And there's a potential for probably 2 gigawatts, 2,000 megawatts of storage in the Central Valley alone. Right? That's what we're going after, right? Yeah, go ahead. So the way we're doing it is compression system, expansion system. When you compress, you store the heat. I think I told you store the heat in hot water. And then when it comes back up, the air gets heated by that hot water, goes through the expansion. What happens in the well itself, right? This is where all the trick is, right? This is all known. Everything on the surface is Siemens will build it for us. So I went to Nuremberg last month and signed a deal with Siemens. They're going to build that surface facility for me, right? They know how to do this. What nobody knows is, how do you do this, right? So here is a well. This is 7,000 feet deep. It was drilled about 100 years ago. The oil layer is here, and the oil is gone. Okay, so what companies like Chevron did was they drilled this 7,000-foot hole. They'll put a metal casing, and then they'll put a cement squeeze on the outer annulus to be sure that nothing leaks. And this casing and the well are sitting there for the last 25 years with no oil. Nobody's working on it. This oil is depleted, and a lot of times it's still leaking methane coming out the top, right? So what we're going to do is put a plug right here. For $50,000, I can put a plug in a well, stop the methane leak. We're going to put sensors. This is not to scale, by the way, right? This is a 7,000-foot well, and fresh water is at about 500 feet, and the saltwater aquifer is about 1,500 feet, and the oil used to be at 7,000 feet. Plug this well, stop the methane leak, put a bunch of sensors to be sure that methane never leaks. because I'm getting air inside. I don't want to combine air with methane. So we're going to make sure that if you ever detect methane, you have an automatic shut-off, you stop the process, right? Then we're going to pump the salt water out of the aquifer and create a giant air bubble here. Okay? In here and here, right? It stretches for miles. And every day we'll only put 1% of the air in and take 1 or 2% of the air out. So it's an isobaric constant pressure operation. The air will sit there in a giant bubble. It's not going to go anywhere. It's contained by the pressure of the aquifer, right? Go ahead. So we've got a 5 megawatt project. We've got University of Southern California, 2 national labs, an electrical power institute, and a oil company operator have all signed up with us. We have a very strong support from the state. Siemens is going to build the surface plant. Subsurface, we have all of our IPs in the subsurface. We expect to raise $100 million, touch wood, next month. And if we get that money, we're going to start the project very soon. Somebody asked me, how much CO2 do you save by building it, right? Because they can't think of energy storage. So I did this calculation it's pretty simple. If you store energy for 16 hours in a 24-hour cycle, every 100 megawatt plant eliminates 280,000 tons per year of CO2 from a natural gas fired plant. And it's 3 times that from a coal plant in India, right? Every 100 megawatt. We want to build 2,000, basically 20 100 megawatt plants in the middle of California alone, let alone India, let alone the Middle East, let alone the rest of America, right? The potential is 20 100 megawatt plants in the middle of California alone. So go ahead. So back to India, right? So what do we need in India? So as I said to you, pumped hydro is what they're working on. So the question is, what is the opportunity for this idea in India? So go ahead. I'm going to skip through these. So one study was done in 2018 by a Finnish, I usually give attribution at the bottom for all my slides. A Finnish company did it. And they say that they looked at permeability and porosity, and they said, yeah, India's got some chance. Go to the next slide. So around the world, wherever you see red, that means there's really good potential for doing what I'm suggesting. You can see in India, it's not very, very much, except notice it's not where the oil is. So they didn't look at oil wells, right? They looked at where there's natural ability to drill a hole and create a storage. So they say it's in Madhya Pradesh and Uttar Pradesh right in the middle, right? You can see US is chock-a-block full of opportunity. Africa has got it, Europe's got it, India has very little. So people are disappointed, but they didn't think about my idea of idle oil wells, right? So if you go to the next slide, a study was done more recently, including the United Kingdom and Malaiva National Institute of Technology in Jaipur, right? So they published this paper a couple of years ago, and they looked at caverns. They didn't look at the previous study, they didn't look at oil wells. They concluded that there are caverns out here in the middle of, again, Uttar Pradesh and Madhya Pradesh, nowhere else in India. And their numbers are just flat out wrong. I have to write to them. They claim that even with that small capacity, they claim there is 11.6 billion megawatt hours of opportunity in India, and they're off by a factor of 10 at least, or 100. So I've got to fix that. But anyway, go to the next one. So where is the opportunity for that idea I'm talking about, right? No one has looked at it in India. Turns out the opportunities are where the old oil wells were, right? We don't want to go offshore like Krishna Godavari Basin, like Reliance's KG Basin. That's offshore. Once you go 50, 75 kilometers offshore, the cost goes up. We can't go there. Bombay High is offshore. Gujarat is onshore in the Kutch region, Saurashtra. Rajasthan, Cairn Energy is onshore. And Assam is onshore. Guess when was the first well drilled in Assam, and what is it called?
Dig Boy.
Yeah. Well, you know why it was called Dig Boy? It's a racist insult. So there's a British guy who's standing there and getting these guys to drill, and the guys weren't drilling fast. He says, dig boy, dig. And we called it Dig Boy, right? I wish you would change the name. So clearly, the oil in Assam, those wells are very old and many of them are depleted, right? The old wells in the Kutch, Gujarat area are also depleted. The Rajasthan wells are relatively newer, although that's where all the solar plants are. And then there's a bunch of other places that are explored for oil. See, the other thing is, if you drill for oil and don't find oil, which is the case often in India, I'll take those wells. What that means is, it's a nice hole in the ground, there's no oil, it's a dry well. Dry wells are even better for me. I don't have to worry about any remnant oil there, right? So what are we doing? So it's Gujarat, Rajasthan, and Assam. We're just starting to look at it. Go ahead. So in summary, I'm finishing up now. I've got 10 minutes for Q&A. So as the world pushes for greater than 20 to 30% renewable energy on the grid, you need more than 6 hours of storage. If you learned anything at all today, India is at 20, America's India are about 20 to 30%. You go beyond that, you need more than batteries. So that's lesson number 1, right? Our national target is 450 megawatts of solar power by 2030. 2 days ago, they came out with the fact that they want 60% renewable energy on the grid by 2030. 60%. We're at 22% now. How do you get to 60% on the grid? Once you cross 25, 30%, batteries are not enough. You need 10 hours of storage. Where are you going to get it? They're looking for mountains and lakes, right? That's what they're doing in India right now, right? So we know that, so pumped hydro is being looked at in India. They've not heard about what I'm doing at all, right? And the 2 studies are very limited, as I showed you. So what I've done is I went to Bombay a week ago. I've talked to L&T. I've talked to ONGC. Nobody knows the answer. It could be that we look and we don't find any oil wells that are ideally suited for this, right? Maybe, but we don't know the answer. So what we are saying is we would like to explore this opportunity to see if it's possible while I'm building all this in California. I personally would like to work with Professor Shankar Narasimhan and GV again, if he's active back in this. We need to pursue this liquid air thing, right? Because that one we could do anywhere in India. And this can go for 10 hours, 20 hours of storage, right? It's more expensive because of cryogenics, but it can be done. I don't know if Professor Venkatratnam is still working in this. He is, right? So I think Professor Shankar Narasimhan from Chemi supports the cryogenic side, the heat transfer side, complementing Professor G. Venkatratnam's brilliance in mixed refrigerants. He's written the book on it, right? So you need both that refrigerant mechanical engineering aspect and the chemical engineering aspect. Those two are combined together to do it. So I'm hoping to work with them. And then basically India needs more solutions beyond batteries, right? That's my conclusion. So if you got nothing from my talk, pretty soon we're going to need more than batteries. We don't have much option but pumped hydro. We're beginning to explore compressed air storage. I'm sure we'll find idle oil wells. There's no doubt in my mind. I'm sure we'll find it. Once we find it, L&T says they will build, own, operate, build the whole value chain. Tata says they'll build the whole value chain. I said, where do you get the wells from? Oh, we'll get it from ONGC. Maybe. So we have to work all those connections, right? So right now I'm too busy building my project in California, but I want to do something in India for this, right? And then if things go as we hope, we want to build a liquid air plant in IIT Madras and see if we can commercialize our own technology there. So I'll stop there. Questions? Any questions, comments, anything? Yeah, please. Yeah, redox batteries I skipped through. There is one of them. The vanadium one is commercial. If you Google it, you can't find too many commercial batteries. Redox batteries have been around since I was born. I can't find enough commercial plants. There are few. They use vanadium. There is some zinc bromide batteries. There's a whole new stuff that's being done. But I don't understand why those 10-hour batteries are not there broadly. I don't know what the reasons are. But oh, I see what you're saying. You're saying the technology is there, the need hasn't been there. Yeah. But remember, the US has got the need today. There's like one vanadium redox battery in the US, right? So if you can lower the cost, and then that is a possibility. Now, redox batteries, as he's asking, basically it is what it is, right? Redox batteries. There are flow batteries too in that. They can go for about 10 hours of storage, right? Now, we can go beyond that, but 10 hours is excellent if you can do that, right? So great question. Thank you. Anybody else? Any other questions?
I have
Yeah.
two questions.
Yeah.
One is that as we are decreasing our dependence on fossil fuels, there is a huge debate on whether we should rely on nuclear energy or not. Like countries like France are still relying a lot on nuclear energy, but her neighbor Germany is shutting down the nuclear plants. Do you think we should have a substantial portion of nuclear energy also in our? Great
question, right? So what he's saying is, I don't know if you all know that when the Fukushima incident happened in Japan, Angela Merkel stood up and said, I'm shutting all my nuclear plants, right? That was not a smart thing to do, right? So Germany is short on renewable power. Guess where they're getting their power from? From France. France is 75% nuclear. They've operated safely. And Germany gets their nuclear power from France. What is the point in not building your own nuclear? So I don't get that. So I think nuclear has a place. Couple of problems with, well, you know the problems with nuclear. One is it's extremely expensive, capital intensive, takes a long time to build. Secondly, the age-old problem is what to do with the spent material. Half-life of thousands of years. What are you going to do? So in America, we used to put it in a place called Yucca Mountain in Nevada. They're like, not in my backyard. You're not going to put it here. So where are you going to take it, right? Somebody thought about taking it on a rocket ship and dumping it in Mars or something. So the problem with nuclear energy is the spent. One is the safety of the reactors. That's getting better, right? They are building small modular reactors that are incredibly safe. They'll shut themselves off. It's not like the old rods dipped in. It's not the Fukushima. It's not Chernobyl, right? Chernobyl is still killing people, right? It's not that. So I believe the small modular reactors will come along. They will be safer, but they'll still be expensive, and I don't know what to do with the spent fuel. So my answer for India is to some degree, right? I think what are we, 5% today, maybe less, right? So I don't even know what, I think we're less than 5%, right? So, 7 gigawatt of installed, and it takes a long time to install, it's expensive. India may get to 10 maybe, and they're nice because they're totally carbon free, right? It's wonderful, and it's 24/7, right? It's always on, right? So it's got a couple of great virtues and a couple of really bad dings. So I don't see India rushing to build a whole bunch of nuclear plants, right? Kalpakam is where we have it, right? So we're going to have 1, 2, 3, we're up to 3 or 4 now. And I think there'll be other places that'll expand. I don't see it being a major solution, right? If you're going to, first of all, if you're going to build all that solar, that's not going to help you. You still have to store that energy, right? So I would say, other than France, it's going to end up being 5 to 10. US is never going to be more than 5%, right? They're extremely afraid of it. 3 Mile Island happened when I was living in Pennsylvania. It's pretty scary, right? So I would say 5% in the US, 5% in India, 70% in France, 0 in Germany. So, you know, and Japan is freaked out after Fukushima. You heard that yesterday, they finally got the water out of Fukushima. They tried to dilute it into the ocean, and China is screaming, saying, we won't buy fish from you. I mean, that's just a little bit of water from the reactor, right? So it's got a whole host of problems. So, any other questions? Anybody else? Yeah.
In your presentation, you talk about reverse thrusting. Hello. Hello, sir. My name is Sarjit. In your presentation, you talk about reverse thrusting. So I'm a student of metallurgical engineering. So
say that again. I talked about what?
You talk about reverse thrusting.
Reverse?
Rusting.
Rusting. Yeah,
okay.
right. Iron air batteries.
So I remember there was a course, environmental degradation of material, and where the professor mentioned that 7% GDP of India is lost due to rusting and degradation of material and all. So do you think that startup can be applicable to
It's an interesting question. I don't know if you can pair the two. What these guys are talking about really is, it's pretty small batteries, right? What they're talking about is having the iron go from iron to iron oxide back and forth, and they're claiming that they could do multiple cycles. The problem is what is the life cycle of that? Do you 100 cycles of rusting and derusting? How long do you do that, right? That's one of the problems. The energy density is another problem. They claim they're high, but $1 billion has been invested in them, and if they are successful, then I would argue that we can look for other sources of rusting. But this is really very small application in batteries, right? So, yeah. Anybody else? All good questions, guys. Yeah, go ahead.
Why only abundant? Hello, sir. I'm Anirban. My question is, why only the abundant oil mines? Why not the other mines that we can easily found in India, like coal mines?
Fantastic question. I was hoping somebody would ask the question. The problem with coal mines is that even with oil wells, I have to be careful that there's no oil left in the pores because I'm putting air there. I don't want to get into flammability issues, right? So we're actually starting with gas wells that are easy to purge the gas. Oil wells we're going to do last because I'm worried about, because there's always oil left in the porous rock, right? With coal mines, you still got coal bed left in there. How do I put air there? So one idea was put natural gas there. So I'm working with the National Renewable Energy Laboratory, and their idea is very interesting. They're saying, okay, compressed air is fine, and you're doing it in saltwater aquifers in California. How are you going to put compressed air in a coal mine or where the oil used to be, they are saying, why don't you use gas itself as the compression and expansion medium? The efficiency is a little lower. So their concept is, so if you go to the Permian in Texas, it is the largest producer of natural gas in America. That's where the fracked wells are, putting giant quantities of natural gas. What do? The production wells bring the gas up at 100 psi. They compress it to 500 psi, and the pipeline carries that gas all over the southeastern United States, right? 500 psi because you don't want that to drop in pressure drop in the line to the point where the gas freezes. You don't want that, right? So that's a typical thing. What our idea working with them is, let's say you have a gigantic pipeline of 500 psi gas going, borrow 10% of that guy at 500 psi, go to a single stage compressor, heat it up to 2000 psi, the gas heats up to 200 degrees centigrade, stick it back where it came from, or the next well where it is idle. So the gas came from a well, a bunch of idle wells are next to production wells, put it where the idle well was, and at night, bring that gas, and instead of expanding it to the atmosphere, you can't throw it away, expand it back to 500 psi and put it back in the line. The concept is borrow some of that gas in the pipeline, compress it, store it underground, bring it back up, and the temperature will hold. You don't have to have heat store and all that. Come back up, expand the gas, put it back in the line. Brilliant idea by NREL, they patented it, right? So we're trying to do that commercial test in the Permian with an oil company, right? So the one funny part, so one of my vice president of technology teaches design in Berkeley. He said the energy you can develop from burning natural gas is 300 times more than compressing it and storing it. I said, but that's not green, I'm green, right? So that's the issue. So as long as you're burning natural gas, you can't compete with it. But if you're not going to burn natural gas, you want a green way to store it, rather than air, use natural gas. So somebody said, what about CO2? So there's a professor in Lawrence Berkeley lab who said CO2 is ultimate because you're doing CO2 sequestration underground in the same oil wells. So why don't you use that as storage? The problem with that is, let's say I compress CO2. CO2 has a very unique quality that if I compress it to a high enough pressure, it becomes a supercritical liquid, right? Which means it packs energy density, it's just low volume. You could store it, and then you have much more energy density when you expand it. The question is, when you expand it, air I vent, gas I put it back in the pipe, what do I do with the CO2? If I take it and throw it back out there, I've killed the project for CO2 sequestration. If I compress it, put it back underground, I've lost my efficiency, right? So somebody said, why don't you take the CO2 that you stored way underground, compress it, bring it back, but store it in another reservoir higher up in the surface. The problem with that idea is that people want to bury the CO2 so far deep that for 100 years, that's the rule in America, for 100 years you should never see the CO2 escape. If I expand the CO2 to 500 bar, the depth of 500 bar CO2 is about, 1,000 feet. I cannot put the CO2 at 1,000 feet because it will leak. So we haven't solved that problem yet, right? But gas we could do. So the answer to your question is, you could compress gas and store it in a former coal mine. I'd be afraid to put compressed air in there for that reason. But there are companies in Australia that are looking at that, right? So we haven't given up on it because India's got a lot of coal mine, more than the oil. So it's another great question. So I think we're almost out of time. Any last? Yeah, there's one.
You're speaking about this CO2 and its fixation. I just want to there is a video on YouTube by a chemist called Adiabatic. He talks about this. You can watch it. I think I want to ask about the commercialization of hydrogen. See, it's very difficult for commercialization of hydrogen fuel in the sense because first thing it's expensive and second thing it's safety protocol. Very difficult in the sense no one wants to have car fitted the bombs in their next to it because it's so.
There are cars running like that in California, but I don't want to bang them, right? So, yeah.
We are living in an industrial world where like companies go crazy for everything. Like how? My question is like how does this commercialization will work? Because let's say the same Ola started this electric bike, but after selling up for 1 and 2 months, we started seeing issues, right? But okay, let's find it. Battery losses fire, but they were able to escape. Let's say water hydrogen tank first. The whole people died. No, that's the survival rate is very less. Right? So how does this commercialization will work in the future?
Yeah, good question. It's hard. No, the Toyota Mirai has been running for several years now, and it's got a. I mean, they make sure that the wall thickness is such that that hydrogen is never going. Even if you smash right into it, it's not going to break, right? That.
The thing is that it's 1 and 2 cars, this product won't be a problem. But as a mass.
Good point. Mass production. I mean, I thought if you had CNG auto rickshaws and stuff in Delhi, that something would blow up. It hasn't, right? CNG is just as bad. It hasn't happened yet, right? So there's a way to do it. But the other way to answer your question. One of my colleagues has got a startup, and my wife's actually working for them. My wife's IIT Madras 1983, worked at Chevron. She's the head of R&D at Chevron, classmate of Sujata sitting here, right? So she's consulting for a company. What they're doing is, I don't know if you've heard of something called liquid organic hydrogen carriers. It's pretty easy, right? So you take toluene and you hydrogenate it. It becomes methyl cyclohexane or whatever it becomes. It takes up 6-7% of hydrogen. Very safe. And you can do that in any refinery, right? Toluene hydrogenation is easy. What these guys have devised it, they've come up with, like a catalytic converter, they've come up with a small catalyst reactor for a truck. And so Kamala will help come up with the catalyst. What you do is you have a fuel tank. The fuel tank has got a bunch of methyl cyclohexane. Okay? You run it through this catalyst, it produces hydrogen and toluene. Okay? So on board, what they found out is they figured out that the size of the tank is such that they can get hydrogen to a fuel cell for 300 miles on a truck. So they're working with Bosch and Cummins to commercialize that. Their problem is fuel cell trucks are not there. Fuel cell cars are there. Fuel cell trucks are not there. It doesn't quite work for cars. So one idea is put the fuel cell in the truck, and rather than a hydrogen compressed to high pressure, use some other benign means of storing that hydrogen, right? So people are, so get creative and think about what else you can do. Liquid organic hydrogen carriers, they're called LOHCs, is one way to do it, right? So, okay, I think we might be out of time. Any comment from you, Professor Narasimhan? Anything that on liquid air that we talked about? Anything that?
The only thing we are not sure about how many hours of storage.
Yeah. Yeah, these guys.
Decentralized ways of
Yeah.
rather than centralized large scale.
Yeah, what these guys in UK are doing is they are promising 10 hours of storage, and they're building, they claim 100 megawatts. I don't think they can go to that scale, right? It's probably more like 10. So what they're saying is I can build 10, 15 megawatt solar plant. It'll provide electricity for 150 houses. So you can do one on the campus as an experiment, but it's not a large scale answer. It's not. So my idea was, I think maybe you can do it in the Tayur campus. It's got a new name now, but something that takes care of the, you got solar panels here. Can you store that in the liquid air and produce power so that
Use it for charging batteries.
you can use it for charging batteries? Exactly.
Batteries right there at the location.
Correct.
Let's say
Yeah.
in a pumping station.
Yes.
You can put it up. These plants are small enough.
They're small. You can put it in every gas station. Yeah. So I still think we should pursue it, but that's another subject for another trip. I'm leaving tomorrow. So, okay. Thank you so much. This is a great crowd, great questions. So thank you.
Now I would like to invite Mr. Nikhil Tambil, the CEO of the Energy Consortium, IIT Madras, to do the honors and felicitate Dr. Ashok Krishna.
Absolutely. Yeah. Thank you very much. Thank you. Thank you.
Ladies and gentlemen, as all good things must come to an end, it seems we have reached ours. On behalf of the ACR office and the Alumni Relations Cell, I would like to extend our sincere gratitude to Mr. Ashok Krishna for taking his time to share his valuable insights with us today. Your presence and words have truly inspired us, sir, and motivated us too. We are honored to have our esteemed alumnus of Chemical Engineering Department from the batch of 1974 to grace the event and enlighten us. Last but not the least, I would like to express my gratitude to the wonderful audience for their participation and interaction. Thank you, everyone.